Good morning, everybody. I'm so excited to share with you today that our lab has developed these brand new state-of-the-art catalysts for Suzuki coupling reactions. What is the Suzuki reaction is a great question. It combines an aryl halide and a boronic acid into one carbon-carbon compound. But whenever I start research, I always ask myself, why is this important? Why does this matter to us? And I'm about to share a statistic with you that the Suzuki reaction accounts for 10% of all pharmaceutical agents created today. So here are 3 examples of diflunisal, losartan, and irbesartan. We have NSAIDs. We treat heart disease, kidney failure, diabetes with these carbon-carbon coupled drugs. You can see right here where exactly they group these aryl groups together with the Suzuki reaction. But how does this happen? It follows a cyclic mechanism that starts with a palladium zero catalyst and undergoes oxidative addition, which then will undergo a transmetallation with the boron compound. And then it will reductively eliminate R1 and R2 together to get the product that we want. And something that I want to point out about this reaction is that oxidative addition is almost always the rate determining step. It requires the most energy, it has the highest barrier of activation. So what do we do when the barrier of activation is too high? We create catalysts. So our group was inspired by Beller, who made these phosphinoimidazole ligands for his palladium catalyst. This group inspired us to make our own phosphinoimidazole ligands. So a previous member of our lab worked on this specific reaction right here for Suzuki coupling of aryl bromides. There was optimization of this aryl group as well as the imidazole and the phosphine. But what was not optimized? The alcohol. In this catalyst, we only use methanol. So our research turns to optimizing the alcohol on our catalyst. So we turned our attention to all different very common alcohols, including ethanol, isopropanol. We also wanted to try diols. We were wondering if it would make a bi-palladium complex, which it did not. It just formed the regular and heterocyclic carbene, which is right here. So then we went ahead and we tested all of these complexes, and they turned out to be all active in coupling of aryl chlorides and our boronic acid. This stands out from our methanol catalyst right here because our methanol catalyst could only do aryl bromides. So then we picked out our 4 best catalysts, which was the N-butanol, isopropanol, a diol, or 1,3-propane diol, and tert-butanol. And then we figured that tert-butanol gave us the best conversion of this aldehyde reaction. We used these particular substrates because aldehyde peaks are really easy to pick out in the NMR and compare conversion percentages. So then we moved to optimization. You may note that we started originally with decently high catalyst loading, up to 10%. But as any good scientist does, you change one thing at a time. So we started with solvents, and of course here we compared to our methanol catalyst. So we started changing solvents, and then temperature. We worked on catalyst loading for a while. But one of the most interesting things that I discovered was by addition of more alcohol to our Suzuki reaction, it actually made it run significantly better. And we think this is because the addition of extra alcohol may either help the base dissolve better, we're using sodium hydroxide, or it could help in the transmetallation step. So I ran some reactions under the conditions of diluting our pre-stirred catalyst by double. and it made our reactions run significantly better. And then the last thing that I want to highlight from our optimization table is that we were able to do this outside of nitrogen glove box. Nitrogen glove boxes are very expensive and really hard to operate in. So what we did is we pulled our palladium and our ligand outside the box and kept running reactions with it, and it was still just as effective outside the box as it was inside the box. That means that we have an air-stable, a benchtop stable catalyst that can be used by now more than just our lab, any lab that doesn't have a nitrogen glove box. And the last thing is that normally we would pre-stir our catalyst, and then we would add it to our reaction. So we would say the catalyst had already formed, add it to the reaction, but we don't even need to do that. We would just add palladium right to our reaction vial, and with the ligand and the addition of alcohol, and it would form in the reaction, and it would still run with perfectly decent yields. So now that we've updated our reaction conditions of our tert-butanol catalyst, we want to test the extent of the reaction. So to do this, we're just now starting a substrate scope. So while there isn't much data to show yet, we have really high hopes. Our goal is variety. We want to have a variety of electron withdrawing and donating groups. This can just show that our catalyst can do anything, not just one thing. We also want to turn our attention to heterocycles, because heterocycles are, as we saw in the first slide, very, very common in pharmaceuticals. So far, we've been able to show decent conversion with more than just our aldehyde. And as we continue our work in the next couple of months, we are really excited to just try a whole bunch of different substrates, as well as pharmaceutical intermediates. Something else that we were really excited about with this catalyst is that the tert-butanol actually exchanges with the methanol. So what we plan to do is take a dye-substituted aryl halide, one end with bromine and one end with chlorine. Then we want to use our methanol catalyst to react only with the bromines. And we know that our methanol catalyst only reacts with aryl bromides, not aryl chlorides. And then in the same pot, or this, it's called a one-pot reaction, in the same pot, we propose that the methanol will exchange with tert-butanol, which is very reactive with aryl chlorides, and we get this product in one or a two-step reaction that requires no further purification. So with that, I want to thank the BYU Department of Chemistry and Biochemistry for giving me this amazing experience, as well as Dr. Michaelis, who has let me work for him for the past 2 years or so. And then my Suzuki group, Alex Larson and Cindy Pettit. And with that, I will take any questions.